Good morning, everyone. The assignment we had for this class was the difference between IP version 4 versus IP version 6. And now we're going to present the video that we have made. Our group is the Tangled. And I'm going to start by making a quick review of the history of IP version 4 and IP version 6. So, the history of the IP protocol can be traced back to its start in the late 1960s, in which the Advanced Research Projects Agency Network, which we know as the ARPANET, was a project which began in the Pentagon. In 1973, TCP version 1 was designed in the spring of 1973 by Robert Elliott Kahn and Vinton Cerf. Then we make a jump to 1980, where the first formal standard, or public, version of IP was the version 4, and we know as IPv4 was created in this year, and the TCP/IP version 4 was also defined in the RFC 760. In 1981, IP version 4 was described in and IETF Internet Engineering Task Force publication RFC 791, and also replaced the old definition of RFC 760. The following year, in 1982, the US Department of Defense declared TCP/IP as the standard for all military computer networking. After this, in 1983, the domain name system was created to make internet navigation easier in November of 1983 through the publication of the RFC 882. After this, the next big event in history of the IP protocol was in 1989, where Sir Tim Berners-Lee invented the WWW, which stands for World Wide Web, which was essentially the standard for URLs, HTTP, and HTML. Basically, this was the year where the internet was founded. Then we go to 1994. In May of 1994, the first RFC document on Network Address Translator, or NAT, was published. In December of 1997, ARIE, American Registry for Internet Numbers, formed as a non-profit corporation. It provided IP registration and allocation in North America. In 2002, LACNIC was established, providing management of internet number resources to 33 territories in Latin America and the Caribbean. In 2011, in February of 2011, the primary address pool of the Internet, managed by IANA, was exhausted when the last 5 blocks were allocated to the RIR. And on August 9 of 2011, AFNIC was the first RIR to implement an inter-RIR transfer policy. In 2012, the RIPE exhausted the last IP version 4 blocks from its available pool of addresses. And in 2015, in January of 2015, remaining IP version 6 utilization hit approximately 5% as measured by connectivity among Google users. And on September 24 of 2015, ARIN ran out of its free pool of IP version 4 addresses. And as for last year, we have that in January of 2018, native IP version 6 utilization hit 20% in January of 2018. The average price per IP of a 16th was approximately $15 per IP. Now that we have reviewed a little bit of the history of the IP protocol, now we're gonna make a quick review of what is the IP version 4 that it is widely used around the world. So, what's IP version 4? An IP version 4 address is a 32-bit binary value. Only 3.7 million addresses can only be assigned out of 4.3 billion addresses. IP version 4 uses broadcasting for transferring packets from one computer to all computers. This probably generates problems sometimes. And the Internet Protocol is designed for use in interconnected systems or packet switch computer communication networks. For more detail, you can Google the RFC 791. IPv4 is the most widely deployed Internet protocol used to connect devices to the Internet. Even though IPv6 is already implemented, there has not been a migration to this new version of the protocol. And the dotted decimation notation of IPv4 is by dividing the 4 octets by dots. IPv4 is one of the most important core protocols of the standard Internet working methods that are being deployed on the Internet. This is basically a connectionless protocol that is mainly used in the packet switch networks. We're going to review a few important characteristics of this version of the protocol. It enhances its support towards video library files and conferences. It is basically an implementation for the connectionless protocol, and it is used in the creation of virtual communication layers over different devices.
The IPv4 packet format has the following structure. First of all, we have the header that it's 20 bytes and the data that is up to 65,535 bytes. The header has the following fields. First, we have the version that defines the version number of IP. In this case, it will be 4 for the IPv4. The h length that represents the length of the header in multiple of 4 bytes. Then we have the service type that determines how datagram should be handled and includes individual bits such as level of throughput, reliability, and delay. The total length signifies the entire length of the IP datagram. The identification is used in fragmentation. A datagram is divided when it passes through different networks to match the network frame size, and at that time each fragment is determined with a sequence number in this field. The flags field, it handles the fragmentation and identifies the first, middle, or last fragment. Then the fragmentation offset, it's a pointer that represents the offset of the data in the original datagram. The time to live determines the number of hops a datagram can travel before it is rejected. It means that it specifies the duration for which a datagram remains on the Internet. The protocol field specifies which upper layer protocol data are encapsulated in the datagram. It could be TCP, UDP, ICMP, etc. The header checksum confirms the integrity of the header values, but not the rest of the packet. And then we have the source address that identifies the source of the datagram, the destination address that identifies the final destination, and finally the options that provide more functionality to the IP datagram. It can carry fields like control routing, timing, management, and alignment.
Well, now we're going to review a little bit of its latest version, which is version 6. So what's the difference with the latest version of the protocol? That an IP version 6 address is a 128-bit binary value which can be displayed as 32 hexadecimal digits. It provides a 3.4 times 10 raised 38 IP addresses. The format and the length of the IP addresses were changed along with the packet format, and protocols were also modified. IP version 6 is also called IPing, and it is the newest version of the Internet Protocol, reviewed in the IETF standards committees to replace the current version, which is version 4. And version 6 is the successor of version 4, which is pretty obvious. Version 6 is often referred as the next generation Internet standard and has been under development now since the mid 90s. Version 6 has become a draft standard in 1998 and later established as an Internet standard in 2017. It is mainly represented as 8 groups of 4 hexadecimal digits, and each group is separated by colons. Now, a few very important characteristics of version 6. It provides support towards storing of an unlimited number of IP addresses and becomes a favorable choice for interaction between neighboring nodes. This is the main solution that this version implements to resolve the problem of the exhaustion of IPv4 addresses. It provides extensive support towards the stateful and stateless configurations. It enhances the hierarchical addressing infrastructure. And as we can see here in this slide, here's the hexadecimal colon notation of IPv6.
The format of an IPv6 datagram has the following fields. First, we have the version, that it's the same as the IPv4 that identifies the version of the protocol. In this case, it will be 6. Then we have the priority that defines the priority of the packet concerning traffic congestion. Then the flow label specifies the certain flow of data. The payload length defines the total length of the IP datagram, excepting the base header. The next header describes the header that trails the base header in the datagram. The next header is one of the optional extension headers, which IP uses, or the header for an upper layer protocol such as UDP or TCP. The hop limit, it has the same functions as the TTL field in IPv4 protocol. Then we have the source address and the destination address that are the same as the IPv4. The first identifies the source of the datagram, and the second describes the final destination of the datagram. Then we have this payload extension header and the data packet from the upper layer that are like the body of the datagram. The key difference between IPv4 and IPv6. Both of IPv6 and IPv4 are very popular choices in the market. Now I'm going to present you some of the major differences between each one of them. First, the IPv6 header is much simpler than the IPv4 header. From the end-to-end connectivity perspective, IPv6 provides much better results than IPv4. IPv4 is a 32-bit IP address, whereas IPv6 is a 128-bit IP address. IPv4 offers 5 classes of IP address, and IPv6 offers the unlimited number of IP addresses. IPv4 offers support to the virtual length subnet mask, whereas there is no support provided for IPv6. IPv4 provides support to the SNMP protocol for system management, but IPv6 does not offer support. IPv6 provides much better multicast and anycast abilities than IPv4. IPv4 header includes space for IPv4 options. In IPv6 header, we have a similar feature known as extension header. IPv4 datagram headers are normally 20 bytes in length, but we can include IPv4 option values also along with an IPv4 header. In IPv6 header, we do not have options, but we have extension headers. The fields in the IPv4 header, such as internet header length, identification flags, are not represented in the IPv6 header. The time to live, a field in IPv4 header, is typically used for preventing routing loops, is renamed to its exact meaning, hop limit, in the IPv6. IPv4 addresses represent the binary numbers in decimal. On the other hand, IPv6 addresses express binary numbers in hexadecimal. IPv6 uses end-to-end fragmentation, while IPv4 requires an intermediate router to fragment any datagram that is too large. Header length of IPv4 is 20 bytes, but the header length of IPv6 is 40 bytes. The option fields in IPv4 are employed as extension headers in IPv6. IPv4 uses broadcasting to transmit packets to the destination computers, while IPv6 uses multicasting and anycasting. IPv6 provides authentication and encryption, but IPv4 doesn't.
Okay, now I'm gonna talk about the National Internet Segments Reliability Research and Report of 2019 of IP version 4. So, this report explains how the outage of a single AS can affect the connectivity of the impact region with the rest of the world, especially when it is the dominant ISP on the market. So, internet connectivity at the network level is driven by interaction between autonomous systems, the AS. As the number of alternate routes between the AS increases, so goes the fault resistance and stability of the internet across the network. Well, this graph shows the IP version 4 reliability per country, and well, as we can see, the United States dropped 11 positions from 7 to 18. Bangladesh is out of the top 20. Ukraine moved 8 positions to number 4. Austria is out of the top 20. Two countries returned to the top 20, which is Italy and Luxembourg, after dropping in 2017 and 2018 respectively. And as we can see in number 1, it's Deutschland, Germany, which has the greatest reliability on IP version 4. So each year there are interesting movements in the reliability ranking. Last year it was written that the overall performance of the top 20 countries had not changed since 2017. Nevertheless, this year we highlight the possible global trend towards improved reliability and overall availability. To illustrate this, we compare the 4-year average and median changes of IP version 4 reliability ratings of all 200. Here's the comparison of the 4-year average.
IPv6 reliability. We have been repeating for years that the mistaken assumption that IPv6 works the same way as IPv4 is the main structural problem of the IPv6 development process. IPv4 after a year remains significantly more reliable than IPv6. There are still countries with poor availability with high partial connectivity numbers in IPv6. Compared to last year, we saw significant improvement in all three countries, especially in relation to partial connectivity. Venezuela was at 33%, China at 65%, and UAE, United Arab Emirates, at 25% last year. While Venezuela and China significantly improved their connectivity by resolving several issues of partially interconnected networks, UAE remains pretty much the same without any improvement. Here we can see a chart for Latin America, a comparative chart of the countries between 2016 and 2017. But we can see that the percentages don't vary very much from one year to another in each country. The progress of the transition in Latin America. The LACNIC, the Internet Address Registry of Latin America and the Caribbean, organized 2 webinar seminars on IPv6 in June. Here, Carlos Martinez said that there are a significant number of countries in South America with IPv6 traffic greater than 1%. He cited examples of Peru between 15 and 20%, Ecuador between 15 and 20%, Brazil between 15 and 20%, Bolivia between 4 and 5%, Argentina around 3%, and Uruguay 1.3%, all with percentages of end users with IPv6 well above 1%. According to the IPv6 report, Belgium leads the ranking with 57% of users with the protocol, followed by Switzerland 42% and the United States 35%. In total, at the end of November 2016, there were 300 million users with IPv6 in the world, representing 8.31% worldwide. All of this is achieved for technical reasons such as avoiding fragmentation and not requiring NATS, network address translation. The mechanism used by IP routers to exchange packets between two networks that mutually assign incompatible addresses. In summary, it consists of converting in real time the addresses used in the transported packages. Here we can see a chart with the share of internet traffic that was IPv6 in Latin America and the Caribbean on October 2019. We can appreciate that Brazil has the greater percentage, followed by Uruguay and Mexico. This chart represents the hosts and the percentage of vulnerability of the IPv4 protocol used by each country in Latin America.
Now, we're going to talk about the top 5 countries with high IP version 6 adoption. It is already known all the advantages and updates that IP version 6 provides in comparison with IP version 4, as we already mentioned earlier several times on this video. But well, IP version 6 also comes with many security features which put it above IP version 4. It was in development since the late 1990s, when the IETF formalized the next generation Internet Protocol in 1998. IP version 6 was finally launched on June 6th of 2012. So the top one in this list, it is Belgium with a 46.6 percentage, and their adoption rate has been steady over the last couple of years. Following Belgium, it is Greece with a 27.6%. Shows a considerable drop in comparison to Belgium. However, it's still higher than other countries in the world. In the third position, we have Germany with a 26.1%. Starting from Germany, you won't see a considerable drop in the adoption percentage between two consecutive countries. Number 4, we have Switzerland with 25.6%. It isn't surprising because Switzerland is known for its brigade of determined coders who don't give up easily. And in the last position, we have India with the 25.4%. So this is a topic that all of us have wondered at some point, and it's, why is there no IP version 5? Well, there actually was an IP version 5. It was known as the Internet Stream Protocol, and abbreviated simply as ST. And it was designed for connection-oriented communication across IP networks with the intent of supporting voice and video. It was successful at the task and was used experimentally. One shortcoming that undermined its popular use was its 32-bit address scheme, which is the same scheme as IP version 4. And as a result, it had the same problem that IP version 4 had: a limited number of possible IP addresses.
To finish this video, we have a chart with the summary of the differences between IPv4 and IPv6. Here I'm going to state the most important ones. First of all, the size of IP address in IPv4 is a 32-bit IP address, and in IPv6 is 128-bit IP address. The addressing method is a numeric address in IPv4, and its binary bits are separated by a dot. But in IPv6, it's an alphanumeric address whose binary bits are separated by a colon, and it also contains hexadecimal. The type of addresses used in IPv4 are unicast, broadcast, and multicast. In IPv6, it's unicast, multicast, and anycast. In IPv4, there is 5 different classes of IP address, from class A to E, but IPv6 allows storing an unlimited number of IP addresses. For the fragmentation, it's done by sending and forwarding routes in IPv4, and in IPv6, its fragmentation is done by the sender. For the network configuration, IPv4 needs to be configured either manually or with DHCP, but the IPv6 has support auto-configuration capabilities. The best feature of IPv4 is the widespread use of NAT devices, which allows single NAT address can mask thousands of non-routable addresses, making end-to-end integrity achievable. And IPv6 allows direct addressing because of vast address space. Then we can state that the security in the IPv4 is not designed for this protocol, but the IPv6 has the Internet Protocol security that it was built into the IPv6 protocol and is usable with a proper key infrastructure. For the packet size, IPv4 size, a packet size is 576 bytes required with fragmentation optional, and IPv6 is 1028 to 108 bytes required without fragmentation. For the optional fields, we have that the IPv4 has optional fields, but the IPv6 doesn't have them, but it has replaced it with extension headers. And finally, we have the compatibility with mobile devices. IPv4 addresses uses the dot decimal notation, so that's why it's not suitable for mobile networks, but IPv6 addresses are represented in hexadecimal, so they are better suited for mobile networks.